Hi, today we will discuss understanding behavior of frame structures. But first, we need to understand our construction materials. For the mud and clay, usually it's uncooked, so normally it is only good for compression, but weak in tension. For the stone, brick, wood, we also use this one, but for the stone and brick, this is normally also good in compression, but not in tension, except for wood or timber, which are really good in tension and compression. Aside from the wood and timber, we also have what we call the engineered wood. Here is the case for the cross-laminated timber. Again, this is really good in tension and compression. As you can see, they use this CLT for the world's tallest timber frame building in Norway. Aside from that, we have the wrought and cast iron. We have the wrought iron Eiffel Tower and the first cast iron bridge in England. And as you know, cast iron is good in compression. That is why Tilford make an arcs bridge. While the wrought iron is both good in tension and compression. Also, we have the reinforced concrete, or I call it confined concrete because concrete itself is only good in compression but not in tension. Normally, the tensile strength of concrete is just 10% of the compressive strength. But if we will confine the concrete, as you can see in the graph, uh, if we confine the concrete or we put some reinforcement, the compressive stress of the concrete will reach as high as around 2 times the strength of unconfined concrete. And of course, aside from the higher strength, the ductility of the reinforced concrete is also high. Also, we have the structural steel. It can be classified as hot rolled steel and cold form steel. If we have to draw the stress and strain diagram of structural steel or a mild steel, you will see initially at zero stress, and as we increase it linearly, hinahinay nga pagsaka, the stress and strain diagram is a straight line. This straight line is usually governed by Hooke's law. Hooke's law is the Young's modulus is equal to the ratio of the stress and strain, or simply Hooke's law is stress is equal to or proportional to strain, where the proportionality constant is what we call the Young's modulus or the modulus of elasticity. In this portion, in this straight line, kung birahon ni mong material, as long as di pa siya kabot sa yield niya, yield strength, buyan ni mong balik pa na siya siyang original nga position or original length. But beyond the yield strength, as you can see, point B, point C, the steel is already yielding. Then as you increase further the loading, the strain and stress will go up. Yeah, until the ultimate strength of the steel. And it will continue to go down as the strain increases, pero wala nakaga-increase yung stress or loading until fracture. For the hot rolled section, we have standard sections. Unlike the reinforced concrete, it can be square, rectangular, or circular with different sizes. Pwede mo pili kamura. But for the hot rolled steel, di nakakapili because this is manufactured in the factory. So they were able to standardize the sections. So most of the standard sections are the angle bar or L shape, double angle, dapat nimong duha, the channel or C shape and MC shape, the pipe, circular man nga pipe, the round tube, the rectangular tube, the white plants. White plants or W shape, na siya, mura siya glitteray actually, pero mas lapad siya kumpara sa is shape. S-shape normally is dili lapad yang plants. Ang iba pa og ubusanan niya mo na plants tawag na to. Wave ning sa tunga gahawid silang duha. As you can see sa American shape, the S shape, mubo yang plants pero ang yang sa ubos ga curve siya. Unlike sa white plants nga parallel lang iyang ibabaw hasta sa ubos. So that's the difference between the white plants and A shape. Normally sa structural we use white plants compared to A shape. A shape you usually use this one in the chassis of cars, trucks, etc. Also we have the M shape, miscellaneous shape. Kung dili siya white plants, dili siya A shape and others miscellaneous siya. Also we have the HP shape. This is uh, usually for piling. Almost square ni siya. Iyang depth o iyang width sa plants halos parehara. So as you can see, almost square siya and this is usually used as its piles. Kung putlo na nimo mga white plants, M shape, S shape, HP shape, mahimo siya nga T-section. So nasa ibabaw empty shape, WT shape and ST shape. Mga katunga na siya sa mga white plants, S shape, M shape o HP shape. Also, we have the cold rolled steel. By the way, structural steel are really good both in tension and compression. So we have the cold rolled steel. Actually, it's how they manufacture it, how they make it. Hot rolled compared to cold rolled steel. Ang hot rolled, samtang init pa siya, giroll na siya, gipurma. Ang cold rolled steel, plate ra ni siya, plain sheet, tapos gipurma siya, nga walay init. So mo nang gitawag siya nga cold rolled steel. Murag ka na ganing atop ganing nga corrugated or bisan ka nang long span nga mga atop, cold form man na siya or cold rolled steel, gi plate ra na siya, ipagi siya sa machine, mapurma din siya. So we have different sections and normally the cold rolled steel or the cold form steel are, the thickness is really lower than the hot rolled sections. This is also good in tension and compression, but of course the capacity is lower compared to the hot rolled section. So normally we use this for lightweight construction. Also we have the tendons. The tendons is also a steel, but it's a high strength material. As you can see, if you compare the mild steel and the pre-stressing steel in the graph, ma-times 2 pa ang iyahang or more than times 2 pa yung yield strength. If you compare it with the, like for example, grade 16 steel, that's 420 megapascal ang yang yield strength. Ang sa tendon is 1,860. So that's almost 5 times ang yield strength sa pre-stressing steel sa mild steel. And as you can see, musaka pa siya, but definitely halos ang iyahang strain is almost the same as the mild steel. Normally, we use tendons or high-strength cables sa pre-stressing. Kato kong gingot ngayon sa inyo, reinforced concrete tapos butangan siya o tendon, birahon ang tendon. Ang tendon is, the concept is mura siya ka ng lastiko, gani birahon ni mong lastiko. Layo-layo siya mabira, di ba? Then, boy, ano mo balik dit siya. The same is true with the tendons. Elastic pa nga mga material gayapon. Biraon nimo siya, then nasa higot diri, higtanday nimo diri. Buyan, gusto siya mabalik sa original length. So, iyang i-compress ang concrete, the whole section of the concrete, pwede siya nga in compression, pwede po the portion of it is tension. We call it the pole pre-stressing and the partial pre-stressing. But nowadays, it's quite common nga partial pre-stressing siya. Naigamay nga tension, then compression na alos. Kung sa beam siya, i-apply nimo just like this diagram. Initially, imo man i-stress musaka imong beam, mo camber siya. But as we apply the loading, the dead load and the live load, munaog siya. So, almost, pwedeng almost tupong or level siya. Unlike sa reinforced concrete, manaog pa na siya tungod sa iyang weight. But normally, ang technique sa reinforced concrete is we have to camber it during construction. So that when we apply the load, manaog na po siya gamay. Aside from that, we have the high-strength fabrics. We use this in structural and especially the aerospace systems where high performance and lightweight structures are demanded. As you know, kung eroplano or any vehicle sa hangin, kinahanglan gaan gud siya. Para at least gamay ra po diyang weight and makalupad siya eksakto. So here we have the basalt, carbon, glass, and aramid. So depende sa inyong gamit. As you can see, the tensile strength of these materials are even higher than the tendon. Kinilang no, sa aramid at zero strain. The tensile strength is more than 2,000 na siya. Atong tendon, giyon ako siya, 1,860. These high-strength fabrics are also useful in structural, but normally nowadays because the price is more expensive than the ordinary material, so we usually use this retrofitting. Kanaganing mag-ayot ta og mga structures because it was designed medyo kulang siya iyang strength in terms of earthquake. So we tend to repair it. We call it retrofitting. Also, we have different nanomaterials for nanocomposites. This is the future. As you will know, the mechanical properties of these nanomaterials are higher than the materials that we are using now. One example is the graphene. Graphene, as of now, is the strongest material, the nanomaterial. As you can see, the strength is more than 10 to the 5 o magnitude. So probably that's around 100,000 megapascal. Kumpara sa tendon karon nga 2,000 ra. And so with the Young's modulus, taas siya. More than 1,000 gigapascal. Ang structural steel, even the tendon, they are almost the same, 200,000 megapascal. So, ayang kalainan mo na mga long span, pagtaas mo hang Young's modulus, gamay ra po diyang deformation. Unlike sa, ikumpara ni mo ang concrete is around 20,000 to 30,000 megapascal yang modulus. Structural steel is 200,000, so that's times 10. Imagine deflection is a function of 1 over EI. Ang E nasa ubos. Remember? So the larger the denominator, what will happen? Mugamay imong result. So that is why kung dako imong Young's modulus, mas maayo gamay imong deflection or deformation. But of course, these materials are still in development, and I hope this they can discover or they can create some materials that is useful in construction. Aside from these materials, I hope you are able to grasp those materials because the important thing about these materials is that you should know the different mechanical properties so that when you design a structure, you should know if it is in tension, compression, or a combination of tension and compression, or mostly moment, or torsion and strength. Depending on the mechanical properties of the material, you will be informed on what to use. Okay, so that's very important. In the design process, I mentioned this to you earlier. We have the mathematical model. Normally, we have the structure and we need to make a mathematical model for that. Or kung di ka ganag mathematical model, we can say structural model. Depende sa inyo. So we have the real structure at the bottom. Straight line siya ang structure. Normally, we use the stick model, meaning kining mga beams pwede ra na to i-represent nga stick. So that's why in our structural model, mura na siya stick. Medyo, anyway, nagyapon siya thickness, but normally sa to ang mga analysis, especially sa manual calculations, straight line lang yun. Isa lang good kalinya lang. Then we can put some of the supports. Here we have a rectangular section, tapos na siya mga hand supports. So this is usually the how we do it. We have the model, or we have the structure. Normally, there should be action. Uh, we call it excitation. These excitations can be loads. Mamaya akong i-discuss sa inyo last time. Uh, Vibration, or settlement, or thermal changes. With these excitations, we apply it usually sa structural model nato, and then we will look for the response. I said the load effects or structural effects, or normally we call it in general response. The response are normally stresses, strains, displacements, stress resultants, support reaction, something like that. Okay, so from the real structure, normally we develop a mathematical model or structural model using a stick method, and we apply the excitation, any types of excitation, dead load, live load, earthquake, wind, vibration, settlements, thermal changes. Then we will find the response of the structural model. Ang atong ginabuhatonon sa structural analysis diri, how to analyze, how to determine this response as we apply the excitation. The structural design process follows this one, the conceptual design, and then the modeling and analysis, and then design and detailing. Normally, in the conceptual design, kiniusay medyo one is controversial because younger architects tends to say they are the the ano say tawag daw na nila, sila daw ang master sa sa design. Anyway, for architectural plans ay ilagay na siya. They are good in architectural design o pagwapa o space planning ana. But normally it's quite useful if we partner the architecture or the architect and the structural engineer. Pagsugod pa lang, pag-concept pa lang, dapat na sa structural engineer. So that the structural engineer can advise the architect on the structural system. Because magsabot man sila sa ilang material gamiton. Concrete, steel, blah, blah, blah. And then mayon si architect nga, this is our conceptual design. Magunaw na po si structural engineer si possible niyang skeleton siyang building. In that way, mas paspas ang process. Unfortunately, unsay kakahitabo kay tungod lagi si architect kay siya man gud prime professional. Siya rin gahimo-himo ya totoo dihatag niya ang plan kang civil engineer. Mukalot na rin ang ulo sa civil engineer. Ano man, magproblema siya sa unay pagputang sa mga skeleton, slabs, okay lang ang slab, ang beam ug ang kulom gyud may problema kaayo. And normally they want, especially sa mga balay, dili tuloy-tuloy nga kulom, putol-putol, and that is not really good sa earthquake. Anyway, that's the conceptual design, and we can move on the modeling and analysis. Normally, diri ang structural analysis, modeling and analysis. We try to model it, structural model, and then analyze. Of course, normally we should have the trial sections because most often we don't know yet the section. This is the problem. It's iterative in nature ang structural analysis and design. So magtag-an sa ka og trial section. Of course, if you have experience, masayo na siya. Pero wala may problema. You can go around tanawong mga building, kung pare-pareha lang, pwede nimong sukdon kung sa kadako yung column. Most probably, mo ang result mo gyapon na diapit. Then, if you have the trial section, you can model, or actually you can analyze dayon. You have to model it and then you can analyze dayon. When the analysis, we use this one for the design and detailing. Malang nakasumpay siya. Analysis, then member design. You have to check if it is acceptable or not. If no, then you have to revise the section. So this is what I'm trying to say. Iterative ang design process. Tagna-tagna. Anyway, kung naka-experience, kaduha nga balik, okay ra. Katulo, medyo sakit-sakit na ng gamay. But if you don't have the experience and you don't follow what I say, nga madto ka sa actual nga structures magsukod, then mga kalima ka unom siguro ka balik-balik. That's hago na kaayo. So, going back, you have to model it again and analyze and then design the member. If it is acceptable, then you need to design the connection. So mao man mo ang design sa member ang connection, then detailing na dayon pag plaster sa mga kung reinforced concrete, pagpataw plaster sa puthaw, ang sa structural steel ay mga plaster sa connections niya, mga stiffeners, and then you can have the final design. So this is usually the process: conceptual design, modeling and analysis, design and detailing. So nata diri dapit sa modeling and analysis. Next time pag mahuman mo sa structural theory, we will do the design and detailing. Okay, so for now we have known the material, and then we were able to do some structural design process. Then we will discuss next the behavior of the structure.